Okay, so last time we discussed basically clipping circuits. So this today we basically try to cover the clampers or clamping circuit. So before moving to these clampers, so we basically need to cover some concepts related to the capacitors. So during the circuit analysis, we found that so if we have this kind of a circuit arrangement, so if we have a capacitor which is basically charged up to V naught value at t equals 0, so then we connect a kind of a load resistor, then the whatever the stored energy of the capacitor is basically released through the resistor, so which we basically define this particular process as the discharging of the capacitor. So this is a discharging process of the capacitor. So we model this discharging through this solving this first order differential equation, and we found that the voltage across the capacitor basically equals to V naught e to the power minus t divided by RC. So this is the behavior of the capacitor, or the behavior of the voltage across the capacitor once it's charged to V naught at t equals 0, and if it is basically discharging through a resistor RL. So this is so for the time. Okay, so this is the discharging process. So we uh, hope you may remember that we start with the Kirchhoff current law, and we develop a kind of a first order differential equation. Then we solve this differential equation by substituting initial values. So later on we found that the voltage across the capacitor can be represented using a kind of a exponentially decaying function like this. So this is the discharging process. If you ask to characterize the discharging process, so this is the mathematical characterization of this discharging process of the capacitor. So then we found that a concept called time constant. So this is basically denoted by tau. So for RC circuits, so the circuits contain basically resistors and capacitors. We define such circuits as RC circuits. For RC circuits, time constant would be the product of R and C. So maybe like you have multiple resistors and multiple capacitors. So if you can simplify the circuit to a single capacitor and single resistor, so then this tau is actually R equivalent into C equivalent. So the C equivalent and R equivalent means like if you have multiple resistors and capacitors, so there may be a kind of approach to simplify the circuit into a single equivalent capacitor and single equivalent resistor. So in that case, this particular RC circuit has a kind of a time constant which is equals to the product of R equivalent and C equivalent. If you have a single resistor and single capacitor, just a product gives the time constant. So time constant basically gives a kind of indication about the rate of charging or discharging. So we found that we can illustrate this time constant. So if this is T, so this is the discharging process. So the initial voltage is V naught. So this is the VC voltage across the capacitor. This is actually behave like this, T or RC. So we found that time constant for this particular RC circuit is a product of R and C. So tau equals R and C. So then we found that this is the time constant. So this is time RC. The value here is V naught divided by E. So once you replace this T with RC, which is our time constant, so then you can easily evaluate the voltage at that point. So at time constant, so the voltage across the capacitor would be V naught divided by E. So this is your time constant. So for example, like if you have a small time constant, so then this discharging process is something like that. So now the time constant is somewhere here. So if you have a time constant which is greater than 0, pretty much greater than, so then this discharging is something like that. So then the time constant will be somewhere here. So then by looking at these three curves, we can basically come to a conclusion. If this time constant is very small, so we can simply say that high rate of charging and discharging. So it basically discharges to minimum very quickly and charges to whatever the maximum voltage very quickly. So then it's something like that. So if it is a charging, it's immediately charged to its maximum, or else it's immediately discharged to its minimum. So this is where this tau or the time constant is pretty much small. So if your time constant is large, so then the low rate of charging or discharging. So it means if you draw it, so it's something like that. So it takes a reasonably high times to charge to its maximum. At the same time, it basically needs more and more time to discharge. Okay. So this is basically charging, this is discharging, this is charging when this time constant is very high, this is discharging when time constant is very high. So now you can see the relationship between the time constant and the time it requires to charge or discharge. Okay, so we will then can come to a conclusion by considering this worst case or extreme scenarios. So these are the extreme scenarios. What happens tau equals to 0 and what happens tau equals to infinity. So this is, so we can mathematically come to a conclusion like what happens tau equals to 0 and what happens tau equals to infinity by looking at this graphs. So if this tau goes to 0, which means your time constant is very small, or it is very close to 0, so you basically can see this kind of a charging process and this kind of a discharging process. So if it is a charging, it's immediately charged to its maximum. If it is discharging, it's immediately dropped to 0. So if you have a 0 time constant, so you can see basically this kind of a rapid charging and discharging process. So if it is the other way, like for tau is infinity, so then what happens? So we can basically argue that if the time constant is infinite or reasonably large, so then we can ideally say if it is a charging, it never charged. Because the time constant is basically infinite, mean you basically need infinite time to charge. So then the charging would be zero charging. So if we focus on discharging, so then whatever the voltage remains as it is, it's never discharged, remains at the same voltage. So hope you get the point. If your time constant is zero or close to zero, we can simply say that so this particular circuit can immediately charge or immediately discharge. If your time constant is very much high, mathematically speaking, if it is infinite, so we cannot find out a set of circuits where this time constant is infinite, but in practical sense, so the time constant is pretty much high. So then the charging, once you consider the charging process, your charging will never happen because ideally it takes infinite time to charge. So at the same time, if the capacity is charged to a certain level, if the time constant is very high, you can assume that there won't be any discharging through the circuit. Yeah, if that capacitor has a zero voltage initially, so you can't see. I mean, it basically simply stay at zero voltage. If it is charged up to a certain level, if it is a discharging process, so if you basically connect it to a kind of a resistor, if the resistor is too much high, it's very high, so then the time constant or the product of C and R is high. So then you can argue with that. So if you connect this a capacitor which is charged up to a certain value to a kind of a high resistance, so the time constant is very high, then capacitor remains at same voltage. So whatever the voltage basically reached is keeping as it is. If that particular capacity is 0 voltage, it simply stay at 0 voltage. If you charge it to 5 volts and connect it to a kind of a high resistor, so then we can argue that this RC product is too much high, so the time constant is high. So then capacitor basically needs pretty much high times to discharge. So then based on this comparison, we can say that the time that capacitor need to drops to voltage 0 is high. So we can assume that so capacitor never discharge. So mathematically, if your time constant is infinite, the capacitor never charged. At the same time, capacitor never discharged. So whatever the voltage that capacitor takes during this previous stage remains as it is. Okay. So again, like for the practical circuits, we found that so for this charging and discharging process, capacitor basically needs 5 times time constant to charge or discharge to its max or min. So it means like we know the time constant is somewhere here. So this phi tau is somewhere here. This is phi tau. So if this capacitor charged to its minimum, it needs 5 times the time constant time seconds. So similarly, if it is a charging process, it basically converges to whatever the maximum within this 5 times the time constant duration. So this is kind of a fact that you can keep in mind. So then if your switching circuit is basically meeting that requirement, for example, we will think of a circuit like this. Okay. So we'll basically connect this kind of a voltage. So this is V naught and this is 0. Now this is the voltage we apply to a capacitor. Okay, so we know that once you apply a kind of a positive voltage, this capacitor basically get charged. Let's assume like okay, so we put these values like this is a periodic signal, so this is basically t by 2, this is basically t. So during this first half of the cycle within the 0 and t by 2 period, so we basically apply a kind of a positive voltage to the capacitor. So then once you apply positive voltage, capacitor gets charged. So we can simply say that it basically charged. So it basically charged. So once you release the voltage, so it means like we basically remove the source from the circuit. So then, so this capacitor is charged to V naught, and then once you release it and connect a kind of a resistive load, so capacitor basically discharge. Okay. So then once you connect the source, again it's charged. Then again discharge once you release the voltage like that. So this is the voltage across the capacitor, VCT. Okay. So let's assume we have kind of a time constant. So then it means like this is basically pi times tau, or this is basically pi times tau. Because this is the time which this capacitor requires to charge it to maximum. So if the time constant is tau, phi times tau should be there to charge it to maximum. Similarly, we can argue that during this phi tau time, so this capacitor discharged to its minimum. So what happens if this phi tau is comparably large to t by 2? So this is phi tau. So this is the time requires to charge. Time requires to charge or discharge to its max or min. It means like if you draw it in the same plot, so it basically, if you draw the charging process, like let's assume this is your phi tau now. Okay. So then capacitor need this much of time to charge it to V naught. So then if you draw this, it's something like that. So this is the profile of this charging process. So this dashed green line represents the profile of the charging process. But at this point, so we basically remove the source from the circuit. So then capacitor doesn't have any external source to charge it to V naught. So it basically plans to charge it to V naught, but in the middle of the process, we basically remove the external source. So then capacitor doesn't have any external source to charge it to its maximum. So this definitely this charging process may hold at that particular time. So then once you draw the actual profile of the charging, it's something like that. It basically charge up to this one, not up to V naught. So this may be somewhere around V naught dash. So it basically charge up to V naught dash, which is less than V naught dash is less than V naught, because now the phi tau is pretty much higher than T by 2, which is the half of the period of the external voltage, applied voltage, or the periodic voltage which we apply. So then we know that a particular circuit needs 5 times tau to charge it to maximum. But during the charging process, or mid of the charging process, somewhere around the T by 2, we basically remove this external source. So then this capacitor doesn't have any external source to charge its internal voltage to V naught. So it basically stopped the charging process the somewhere around here. So then the capacitor is basically charged to V naught dash, which is less than the initial source voltage V naught. So similarly, you can argue like for the discharging process also, it needs basically phi tau. So it needs this much of time to discharge on this. So now this phi tau is greater than T by 2. So let's assume this is the phi tau. So then capacitor needs that much of time to discharge to 0. So if you develop the project profile of this discharging process, it's something like that. So but again, so this before it drops to 0 voltage, we again connect the external source. So then suddenly this discharging process should stop at somewhere else and try this capacitor charging. So this discharging process is simply stop at here, and again capacitor try to charge it. Okay. So now the profile is something somewhere around here. So then it's again charged to somewhere here, which is close to discharge somewhere here likewise. Because keep in mind this voltage may be simply developed because here the initial voltage is 0, but here initial voltage is not exactly 0, it's slightly above the 0. So then if you refer these two voltages, so this voltage is slightly higher than this one because the initial voltage is not exactly 0. Here this development is starting from 0 and moves to V naught dash, but here it starts from a value which is slightly above 0, and this is basically go up to slightly above V naught dash. Similarly, discharging points also same, because the time constant is same. It means like we never change the resistance and the capacitance of the circuit, so the profile or the shape of the profile or the gradient of the profile is same throughout the process. I mean, like this profile, this is V naught e to the power minus T over RC. This is also same, but these two charging process, the difference between these two charging process, here the initial voltage is 0, here the initial voltage is not 0, it's slightly above 0, slightly above 0. So then if you keep the profile as it is, if it means like your resistor and the capacitor keep in the same value, so then this value is slightly less than this one, because initial voltage is not at 0 for this place. So it's slightly developing. Once you apply kind of couple of this kind of cycles, your voltage may reach to after certain cycles. But keep in mind what I want to highlight here. Yes, tell me. So what we can't see. Can you see the shared screen?
Yes, sir, we can see.
Okay. So the point. Okay, so this is the point. So this is the point. Can you see now? So this is the point.
Yes.
Yeah, you don't need to focus on the pointer. So this is the point where this during this first charging cycle, the voltage is at actually. So first charging cycle, so it basically moves up to this from 0 to V naught dash. So this is the second charging cycle. So this is the second charging cycle. So during the second charging cycle, so here the voltage it's slightly above V naught, 0. I'll put like 0 first for the convenience, and it moves to it's like double dash. So V0 double dash is actually slightly above V naught dash. Why? For this particular charging process, capacitor charge from 0 to V naught dash. For the second charging process, it's not start at 0, it's slightly start at a value which is slightly above 0. So then if the profiles are same, profile means the voltage, this is not charging, sorry. So this is the profile for the charging. So if you keep this R and C as it is, and the source voltage we know as it is, so this profile or the curvature of this profile is remains same. So then I mean like the whatever, if it is linear, this gradient should be same. So then definitely if you start from 0 and here if you start slightly above from 0, so then this ultimate voltage you reach here is slightly above than. So that's the point what I need to raise it. It means like after a couple of charging cycles, so the voltage across capacitor may gradually reach to V naught, but not during this first couple of cycles. So anyway, what I want to highlight here is if the voltage you apply externally, so the period of this external supply T or T by 2 or the half period, if it is pretty much less than the phi tau, this is the phi tau is the duration that capacitive circuit requires to charge is to maximum or minimum. If this is very high, so this capacitor never charged to its maximum or it never charged to its minimum, discharge to its minimum, because it needs more time to charge and discharge. If it is the other way, if this quantity is greater than phi tau, so it means this kind of arrangement. So then within the given time, so this capacitor and the capacitor discharge it's to minimum and charge is to maximum. So if it is something like, so if you have this kind of arrangement, so this is the charging process. So in this case, this is, let's assume this is phi tau. So this is phi tau. So this is T by 2. Now T by 2 is larger than phi tau. So then whatever the capacitor can charge it to maximum and discharge it to minimum within the given time frame. So if it is the other way, so the capacitor, so we basically are not providing enough time to the capacitor charge it to maximum and minimum. Hope you got this point. Okay, now based on this, so we'll try to explain the behavior of this clamping circuit. So based on this scenario, so we'll try to understand how this clamper operates. So we have a kind of a capacitor here, and we have a diode and a resistor here. It's R, D, C. So let's assume we basically apply this kind of a voltage. So this is minus Vm plus V. It's a Vm. So the input signal is a kind of a periodic square wave. This is your input signal. It's a periodic square wave. And we have a capacitor which is initially at 0 voltage. The voltage across the capacity is 0 at the initial level. And D is a kind of a ideal diode. And we have a resistor also in the circuit. Okay. Now we'll try to see what happens to the circuit if you externally apply this kind of a square wave to this RC circuit. So let's think about during what happens to the circuit during this first negative cycle. This is negative, this is positive, this is negative. So this is negative first, this is positive first, this is negative second. So I'll use that notation for the. So we'll first consider negative first cycle. Okay, negative first means this cycle. So if you draw the circuit, so this is the circuit actually. So we basically apply negative voltage across the input. So then the direction of the voltage is like this. Here it's minus, it's plus. The voltage you apply is Vm. So it's a negative voltage. So we basically capture this negative by changing the polarity and put the magnitude here. So it's a negative voltage. Now we have a diode. Now, by looking at this, you can basically identify two parts. One is this through the diode. So the second one is through the resistor. This capacitor gets charged. Okay. So we have two parts. One is through the diode. So the other one is through the resistor. Okay. Let's assume like if it is through the diode, so we should aware that this diode should be forward biased to make it this capacitor. We want to make this diode forward biased to see a charging process of the capacitor. So if this diode is reverse biased, you don't see any current flow through the circuit. So it's act as a kind of open circuit scenario. So then this capacitor never charge. So then definitely this diode should be forward biased to make this capacitor charge. So how do you verify whether it's in a forward direction or reverse direction? So we can apply the previous concept we have used to verify whether it's forward or reverse. So this is the polarity of the diode. This is minus, this is plus. So this is the voltage across the diode. So then we can claim that. So how do you evaluate the exact voltage appear across the diode? We first remove this diode and evaluate the voltage across this diode. So if you consider this block, this circuit, so we can simply say that once you apply Kirchhoff voltage law, VD should equals to Vm, because initially voltage across the capacitor is 0. So then there won't be any charge across this capacitor. Then we can assume that at that particular time capacitor acts as a short circuit element, because the voltage drop across capacitor T equals 0 is 0. So then it means like the voltage or the potentials at these 2 points highlighted in blue are exactly same. So that's why the drop across these 2 plates is 0. So it means this acts as a short circuit element at T equals 0. So then there won't be any other drops. So whatever the voltage appear across input is simply appear across the diode. So this is the case. So this is greater than 0. If it is an ideal diode, we can simply claim that. So to make this diode forward bias, we know that VD should be greater than or equals to 0. So if you plug it here, we can simply say that Vm should be greater than or equal to 0. Ideally, Vm is greater than 0 because it's a kind of a non-zero voltage. So this is, so then we can simply claim that definitely during this negative cycle, diode is forward bias. So if it is ideal diode, so we know that diode can be replaced with a short circuit element. Okay, now this diode is forward bias and it acts as a kind of a short circuit element where your resistance is pretty much equals to 0. Short circuit means your the circuit of that particular component, short circuit element, is pretty much 0, or you can say that it's exactly 0. This is for the circuit through this diode. So then we will consider the circuit through resistor. So we have a capacitor and a resistor, so there may be a chance to charge through the resistor. So in this block, we easily find that there is a RC circuit. So this is your R and this is your C. So then let's assume, for the time being, to explain this scenario, let's assume this RC constant or the time constant is pretty much high. It's very, very large. Okay. So if this time constant, which creates once you connect this RC circuit, is pretty much high, you can argue that due to this time constant constraint, this capacitor never charge or discharge. Let's assume that time constant for this particular circuit, RC circuit, where you have this resistor and this capacitor in, assume that time constant is very, very large. So then we can argue that So this time constant of the capacitor is high, very high. So this capacitor never charged or discharged for this particular circuit. If you connect this circuit or through the resistor, whether you apply a voltage across the input terminal due to this high time constant value, so this capacitor never charged. So keep in mind, if you connect this capacitor across this resistor, it never charged or it never discharged. Why? The time constant is very high. So this is the assumption we made throughout the discussion. So the time constant of this RC circuit is very high, and during that period when we have this RC circuit, this capacitor never charged and capacitor never discharged as well. So this is the assumption we made throughout this discussion. So without this discussion or without this assumption, so whatever the logics we build later on may not be valid. So keep in mind, so this should be there as assumption, practical assumption. Otherwise, we cannot build the logic to develop this or explain the circuit. So this should be there. This is a must. So the time constant of this RC circuit is very high, and hence this capacitor is never charging or never discharging. So based on that assumption, we can conclude that this is not the path where your current flow in, because so this acts as a high resistive path. If it is a low resistive path, definitely you can see a current flow through this one and capacitor gets charged. But due to this high time constant, this path is not valid to flow the current. So this is the path where you can see a current flow. So then whether you connect a resistor and a diode, if this diode is forward bias, then you definitely their current flow is through the diode, not through the resistor. So it's then definitely this current flow is through this one, not this one. So keep in mind, to generate a current through the diode, this should be definitely forward bias. If it is reverse bias, so you can't see any current. So if you have two paths, one is through the diode and the other one is through the resistor, if this diode is forward bias, so we can argue that so it induces a kind of a zero resistance path. So then compared to that, whatever the resistors you connect in this path creates a high time constant to the circuit. So then if you can simply say a time constant create due to this diode capacitor circuit is very small compared to the time constant which creates through the capacitor and a resistor. So based on that, we can simply say that current flows through the forward bias diode. Okay, hope it's clear, because so once you consider the first negative cycle, you feel like there are two paths. One is through the diode, so the other one is through the resistor. So then which path you should select? So then we build argument. So once you connect a resistor, the time constant if particular RC circuit creates is very high. So if the diode is forward bias, it introduce a kind of a zero resistance element. So then the time constant would be very small, because your resistance value is pretty much small. So the RC product would be very small when the current is flowing through the forward bias diode. So then you don't have this circuit in the, let's simply remove this circuit component. So whatever the behaviors basically depend on this diode and a capacitor. So we know that this diode is forward bias, and we can simply replace this diode using a kind of a short circuit element. So then what happens to the capacitor? So capacitor is basically charged to Vm. So this capacitor we see is basically charged to Vm. So if you plot these two, so this is your, let's assume, so this is your input, so this is your, so this is the voltage across the capacitor VC. Hope it's clear. It's immediately charged to its maximum Vm because the time constant is very small, because this diode is getting forward bias and introduces zero resistive path. So then capacitor gets immediately charged to Vm during this negative cycle. So see what happens for the negative positive cycle. Okay, next we consider this block. So it means first positive cycle. So then, so you have capacitor, resistor, diode. Now the voltage is something like that. This is Vin. Vin is equals to Vm. And what happens to the capacitor? So this capacitor is charged to Vm, because in the previous cycle the current flow is somewhere like this. So then this should be charged as positive and this should be charged as negative based on the passive sign convention. We know that. So the current is basically entered to the node through the positive node and leaves through the negative node. So then capacity basically charged to this plate is charged as positive and this is basically charged as negative up to Vm. So this is charged up to Vm. So it's depicted here. Next, so this, now I'm referring the second half cycle, positive first cycle. So the capacity is already charged to Vm. Now we have a resistor and a diode. Now again we have two paths. Either this current flow may through the diode, may through the resistor. So we'll see whether diode is accommodating this current flow. So if this diode is forward bias for this particular cycle, also then we can claim that the diode may act as a kind of a short circuit element to facilitate this current. If the diode is reverse bias, we can argue that, so this diode is reverse, so it acts as open circuit element, so then there won't be any current flow through the diode, so it's act as an open circuit. So we'll see first whether this diode is forward or reverse. So this is your diode draw. So we'll apply Kirchhoff voltage law for this part, capacitor, KVL through diode. To find the exact voltage appear across the diode. So if you apply the Kirchhoff voltage, we can see like Vm, which is your input, Vin, which is actually Vm, plus the voltage across the capacitor. Now it's charged to Vm plus Vd should equal to 0, or we can say that we open circuit, whatever. So this is the actual voltage. We remove this diode first, and so we'll do this VOC, and this is VOC. Okay, so then open circuit voltage across these two diodes is basically minus 2 Vm. So input is again Vm, then the voltage across the capacitor again Vm. So the open circuit voltage across these two terminals basically 2 times negative 2V minus 2V. So this is the actual voltage appear across the diode now. So this is less than 0, and diode definitely should be reverse bias. Because we know that if it is ideal diode, to make it forward bias, we have to apply a voltage which is basically greater than or equal to 0. If we want to make it reverse bias, we have to apply a voltage which is less than 0. Now we apply a voltage which is less than 0. So then definitely during this first positive cycle, that is reverse bias. Okay. If this diode is reverse bias, this is basically open circuit. Okay. Now the only path possible is through the resistor. Now diode is reverse bias. Only path possible is through the R. So what happens now then? Now this diode get reversed. So you will ended up with a circuit contains this capacitor and a kind of a resistor. So based on the previous assumption made, so this RC constant or the time constant is pretty much large for this particular circuit, this circuit, RC circuit. So then we can argue that so capacitor never discharge through the resistor. Because RC constant is too much high. So then this capacitor basically charged up to Vm during this first negative cycle. But during this first positive cycle, so due to this high RC constant, capacitor cannot discharge through the resistor you introduced to the circuit. So the whatever the voltage stored inside this capacitor remains as it is, because the whatever the resistor you connect to this circuit creates a high time constant which leads to a zero discharge. So then the voltage across the capacitor remains as it is. Okay. So what happens to the input voltage, output. So let's assume if we define the output across this resistor V out, what happens during this first negative cycle? This diode get forward bias, then definitely this is act as a short circuit element, then the voltage across the resistor would be 0, because so diode and the resistor are parallel. Once this diode forward bias are replaced with the short circuit element, the voltage across the resistor would be ideally 0. So then during this first negative cycle, this is the output voltage, V out. So the during this first positive cycle, so diode get reverse bias and this is open, and this whatever this RC circuit creates a high time constant, and capacitor never discharges through the resistor. So whatever the voltage that particular capacitor acquires during the previous cycle remains as it is. So then what would be the voltage across the resistor? So this VR should be the voltage V out is basically sum of this input plus the voltage across the capacitor, Vm plus Vm to Vm. Now during the second cycle, your input voltage jumps to 2 Vm because the output voltage basically would be the sum of the input plus the voltage across the capacitor. So it simply jumps to 2 Vm. So now we'll consider the second negative cycle as well. For the clarity to see what happens to the circuit, so we'll basically check the second negative cycle as well. So the second negative cycle, negative second. Now I am referring this. So we have capacitor, resistor, diode. Now the input is something like that. This is already charged to Vm. So we have R and D. Okay. So what? So similarly, in the previous state as well, so we have two options. So there may be a current flow through the diode or maybe through the resistor. Now we have to investigate which path is ideally practical for this scenario. So first we check whether this diode is conductive or not. If it is conductive, it means your diode should be forward pass. If it is not conductive, your diode should be reverse. So we will just evaluate the open circuit voltage. Okay, apply Kirchhoff voltage law. So we have Vm here, we have Vm to the down. So if you apply Kirchhoff voltage law, VOC plus Vm across the capacitor minus Vm should be equal to 0. So then the open circuit voltage should be ideally 0. Okay. So then the actual voltage across the diode is 0. During this block, diode is forward bias. During this, diode is reverse bias. So it means my screen is not sharing. What about now? Can you see the screen? Still it's there. Can you see? So we can't see the screen. So still you can't see? Still you can't see. Okay. Okay, so
Yes, sir, we can't see.
so you can't see, no? So I'll drop the session and log into the Zoom again. So otherwise,
It's still not visible.